Yeah, this is a short review of how to dimension a wastewater treatment plant, the process tank, for removal of organic matter. So we have a system, an activated sludge plant, where we want to decide how big an aeration tank do I need in order to have a pretty efficient removal of organic matter, BOD. So I've given some data here, some quantities of BOD at the inlet I need to know, how much is arriving, I need to know about the flow. I have outlet criteria for BOD less than 30 milligram per liter as an 85 percentile, and also an outlet criteria for suspended solids. If I'm looking at the load of organic matter and the flow, well, I could calculate approximately the concentration at the inlet. So I see with 350 milligram BOD at the inlet and 30 at the outlet, I need more than 90% efficiency, 90 to 95, maybe 95% efficiency. So if I'm looking at a curve that tells me something about efficiency for BOD removal as function of FM ratio, I can see as soon as I go down below an FM ratio of 0.3 or in that area, I get up to pretty good removal rates. And the reason why it looks a little bit like a little muddy here is because the clarifier also has a significant effect of how much organic matter is removed. But the biological process will remove the dissolved organic matter very efficient if I'm having an feed to microorganism ratio of, say, 0.25 kilogram BOD per kilogram VSS per day. So that'll be my design choice. Kilogram BOD per kilogram VSS per day. The FM ratio is defined as the amount of food, BOD in the inlet, divided by the mass of sludge. So I'm looking for the mass of sludge here. So I could isolate that and say, well, the mass of sludge in the bioreactor equals the mass of BOD the inlet divided by the FM ratio. Both of whom I know. I've got 600. I will use the 85 percentile for the design purpose because at that load I should be able to perform according to the requirement, because I'm only allowed to exceed the requirement like 15% of the time. So that will be an appropriate number to get 600 kilogram of BOD per day, and the FM ratio being 0.25 kilogram BOD per kilogram VSS per day, and the output here will be 2400 kilogram VSS. So this is the amount of mass of sludge I need in my system. So let's say the clarifier has been dimensioned for a certain concentration of sludge arriving. So let's say we have an XA of 4 kilogram suspended solids per cubic meter as a design basis here. That's what we would like to have in our process tank as well. I need now to convert this to know how much that has to be in kilogram VSS. So I know that a typical ratio between VSS and SS is around 0.8. So there is 0.8 kilogram VSS per kilogram SS in typical activated sludge without chemical sludge. So that gives me the ability to calculate XA in a different unit. So that becomes 3.2 kilogram VSS per cubic meter. Now I can calculate VA. So using 1 and 2 gives me an opportunity to calculate VA, namely 2400 kilogram VSS divided by 3.2 kilogram VSS per cubic meter. And then I get my process volume of 750 cubic meter. So now I've got my VA, so I'm practically home. Could be interesting to see, well, how much sludge am I going to deal with? So calculating the mass of excess sludge production. Doing so, I would like to know the easiest way forward is to try to calculate the mass of the total sludge production, which is equal to the yield constant times the mass of BOD in the inlet. A yield constant for a plant like this, well, I need to go to the literature, try to get some heuristics, some values. That could be this scheme here, where I've got the FM ratio here for these sort of medium loaded plants. I've got the ratio between suspended solids and BOD in the inlet. I don't know, I haven't looked into that, but the normal range here is between 1 and 1.2. So I'm around here, my 0.25, so I get a yield constant around 1.1 kilogram of SS per kilogram of BOD. So that's what I'll assume, that I get 1.1 kilogram sludge produced per kilogram BOD at the inlet as food. So that's what this is, the inlet load compared to the inlet load. So putting those numbers in, 1.1 kilogram SS per kilogram BOD, and now I'm looking for the average production of sludge, so I should use the average load. So that's 550 kilograms suspended solids per day as the average sludge production. Now the sludge production is the sum of the excess sludge production and the sludge in the outlet. So if I'm taking, looking at what I've got here, where I could say, well, I could maximum have 30 milligram per liter, so probably in average I will have something less than that. So I say my excess sludge production, or sorry, the mass of, the excess sludge production, that's the total sludge production minus the amount of suspended solids in the outlet. So that's the 550 kilograms suspended solids per day minus an average flow, so 1400 cubic meter per day. And then something probably a little less. Let's assume I have 20 milligram per liter, so 0.020 kilogram suspended solids per cubic meter. So that gives me 20, let's see, 1400 times 0.02, 28. So 550 minus 28, 522. That is the excess sludge production I need to deal with from this plant. I could also look for the sludge age. What would that be? The sludge age is defined as the mass of sludge in the process divided by the sludge production. In this case, I have 2400 kilogram VSS in my system. I have 0.8 kilogram divided by 0.8 kilogram SS per kilogram, 0.8 kilogram VSS per kilogram SS, and then my 550. So that's 5.5-ish days here. So that's about it.